I'll make you the host again. Yeah. So
Yeah,
you are the host now. You can share your screen and this
yeah,
is hand over to you.
yeah. Thank you, Raghu. And hi, guys. Good evening. First of all, I'm very sorry. There was a problem with audio settings in my system, so I delayed the session for 30 minutes.
No.
My name is Venugopal. Like I'm having overall 10 years of experience in production and control design. I've worked with Indian grids as well as Fin grid, national grids, and other other countries. For also, I extended my production and control system design on the substations. So just I will share my screen. Please let me confirm. Can you confirm anyone is my screen is visible?
Yes, sir. Yes, sir.
Yes,
Yeah.
sir.
Thank you. Like next couple of days and maybe next 1 week or 2 weeks, I will take you all up to this protection and control concept, we generally using in substation design, and I'm going to cover like what are the faults and why we require the protection and control, what is the history of protection and relays, and what are the main components in the protection relays, and feeder protection, transformer protection, bus coupler, bus sectionalizer, bus bar protections. That all I will cover in the next coming slides. So
Okay.
just I will
Yeah, great.
Yeah, just I will start with the faults. Just I will give brief introduction about what is fault and types of fault. See,
Just one when just 1 second. Could you please maximize your screen? I think this screen is not maximized.
now is that okay?
I think we have. Did you use the full screen?
Yes.
It's okay.
For others, it is okay. For other, the
It's
screen is
okay.
okay.
It's okay. Yes, sir. It is okay.
Okay, might be so my local computer problem then. Okay, okay, fine. Yeah, okay,
Can
go. Yeah, yeah.
can we go to topics?
Yes, yes, yes. Go.
Yeah. Okay. See, then I hope that you are already aware of what is substation and how the system is interconnected from generating stations to the distribution station. Okay. So if we check in this, if we check this complete picture diagram, here we are having generating the power, and again we are upgrading the voltage by using the generator transformer to the higher voltages, and from the higher voltages it will be distributed like we're transmitting to the nearest consumer station, and from there again we're reducing and we're connecting to the user purpose. So in between we're having multiple substations. Okay, so we can call that as the interconnecting substations under transmission and distribution, and it will be connected around the complete power systems. So when you are delivering power to the consumer, it is very important to ensure that the quality of the power should be very high, and also interruptions should be very less to the consumers. So how we are ensuring this is because the transmission, most of the transmission line in India and as well as outside the countries, it is exposed to the environment. So okay, as it is exposed to the environment, there is a lot of chances of the faults. So fault is nothing but because of the wind and because of the rains and because of lightning strokes. So the fault will happen on the systems. The fault is nothing but any abnormal conditions in the power network due to short circuit or overload or insulation failure of the devices, which leads to over voltages and as well as currents into the unacceptable level. Each and every equipment in the power system is defined to the some particular value. If you consider the circuit breaker, it will be manufactured for 4000 amps and 50 kA per 1 second. If it is going beyond that, and if the equipment cannot withstand, if that current is crossing more than 53 kA and more than 1 second. So before that, we should interrupt the circuit. So how we are interrupting is that purely depends on protection and control devices which are using in the substations. Okay, so types of faults we can see in the system is we can have two types of fault, that is symmetrical fault and unsymmetrical fault. Symmetrical fault is a balanced fault with the sinusoidal waves being equally about their axis and represents a steady state condition. For example, if there is a edge switch in the substation, if you are closing wantedly into the generally a switch will be in open condition, but when the circuit is energized condition or substation is in live condition, if you close the if you close the edge switch, so that all the three phases will become shorted and that will be connected to the ground. So that we can call it as a symmetrical fault. And coming to this unsymmetrical fault, which displays the DC offset, transient in nature and decaying to the steady state of the symmetrical fault after period of time, as shown in this picture. So best example for asymmetrical fault is the transient fault which occur in the transmission line. If there is any lightning stroke which happened on the transmission line, then first 2 to 3 cycles, the current in the transmission line, it will be very high because it contains both sinusoidal current as well as DC component. So the DC component that will decay after 2 to 3 cycle, and the fault will be cleared once your circuit breaker is gets opened. And also we can consider transient faults and permanent faults. Transient faults are faults which do not damage insulation permanently and allow the circuits to be safely re-energized after a short period of time. So that generally we can say that auto recloser of the circuit after a fault. And typical example would be an insulated flashover following a lightning strike, which would be successfully cleared on opening the circuit breaker, which could then be automatically closed. Transient faults occur mainly on outdoor equipment where air is the main insulating medium. And permanent faults, as the name implies that, as are the results of permanent damage to the insulation. In this case, the equipment has to be repaired and recharging must not be entertained before repair or restoration. So as per the data which is available from the different countries and the over a period of last 15 to 20 years or from the last 50 years, if we assume that. So these are the chances of the symmetrical fault and as well as unsymmetrical fault. If you consider the total 100%, then unsymmetrical fault will be placed more more percentage in the power system faults. So that will be line to ground faults. Here you can see this line to ground fault. There will be chances of 70 to 80%, and line to ground, sorry, line to line there will be 15 to 20%, and double line to ground faults there will be 10 chances, and triple line fault and triple line to ground fault there will be 2 to 5%. So these triple line and triple line ground fault, because it will happen mainly because of the manual mistakes. So because when you are doing the substation maintenance, and if you are forgot to open air switch and you are energizing the system, then once you energize it, as you are already closed the air switch, then fault will happen and that will trip the circuit breakers. Now, occurrence of fault, mainly it will cause interruptions to the power supply to the consumer, because they are the end users. So they need quality of the power. So, and substantial loss of revenue due to interruption of the service and loss of synchronism between equipment to equipment or substation to substation, or one system to the another system, and widespread of blackout due to tripping of multiple lines and generators, and also extensive damage to the equipment because of higher voltages and higher currents that cannot withstand by the equipment, and also serious hazards to the personnel when when particular site, like site in charge or site supervisor or site technician is working at the substation. If there is a fault on the system, if it is not cleared within short time, then that also affect to the person. Then why we need the power system protection? So power network is built to deliver quality and continuity of power to the end user. It's very difficult to provide continuity of power supply to the end user without any protection system, as most of the power network is exposed outside and have chances of lightning strike, short circuit, and insulation failure of the equipment due to bad weather conditions. And the protection is system is nothing but we can have the special equipment is normally installed to detect the faults in the system, and that can be possibly happen in various sections of the system, and to isolate faulty section so that interruption is limited to the localized area in the total system covering various areas. The special equipment adapted to detect such possible faults is referred as a protective equipment or protective relay, and the system that uses such component is termed as a protection system. And protection relay is nothing but is the device which give instructions to the disconnected faulty part of the system. This action ensures that the remaining system is still fed with the power and protect the system from further damage due to the fault. Hence, use of protective apparatus is very necessary in the electrical system, which are exposed to generate, transmit, and distribute power with least interruptions and restoration time. It can be well recognized that use of protective equipment is very vital to minimize the effects of fault, which otherwise can kill the whole system. And the basic requirement for the protection relay, whichever you are selecting to protect the lines or to detect the faults, you should have the selectivity, and you should detect the and isolate the faulty items only, because you should not trip the healthy sections. You should trip only the faulty sections. So that's the reason the selectivity is very important for the selection of particular protection relay. And also stability, to leave all healthy circuits intact to ensure continuity of the supply. And also, like speed also, it plays a major important role when you are selecting the relay for the protection systems. So to operate as fast as possible when called upon, like when you are called to the protection operation, it should be operate as fast as possible to minimize the damage, production downtime, and ensure the safety to the personnel. And also sensitivity to detect even smallest fault in the system and current or system abnormalities and operate correctly at its settings. Guys, is there any doubts till this point?
No, sir.
Okay. Okay.
No, sir.
Yeah, thank you. Now, if it comes to if you go to the history and types of protection relays, like before invention of numerical relays and the protection relays in the olden days, like if you go to the 1950s or 1960s, first the protection is started with fuses. So fuses used for lower voltage levels to protect the devices. Fuses will sacrifice its life and blown out during overload or short circuit conditions. But the problem with the fuses is the manual intervention is required to replace the fuses each and every time when it is blown out. Okay, so then in that case the outage time will be more. So to reduce that, next MCB is invented. So MCB is nothing but miniature circuit breaker, which is have capability to short circuit, like to protect from the short circuit condition as well as from the overload conditions. Okay, and now in the later stage they are, because the MCBs are rated up to 125 amps and maximum 200 amps. So when you are going with the 400 volts and as well as some 2000 amps and 4000 amps, these MCBs are no more useful. Then later they invented molded case circuit breaker. This circuit breaker is an it can be come up with automatic electrical device. It is a type of circuit breaker that protect the circuit from overloading, short circuit, and current surges. And it is an advanced version of miniature circuit breaker MCB since it operates like one. However, it offers extra features that it makes superior circuit breaker, such as a remote closing and adjustable trip settings. That is, current settings and time setting can be adjusted according to our needs. As it is inbuilt equipped with the motors, we can operate that motor mechanism from remote end also, like from by using the SCADA system or from the PLC system, we can close and open this MCCB whenever you required. So in the later case, now see, fuses MCB and MCCBs can be useful for the lower voltages up to 400 volts. But if you go to the 11 kV system, 130, 66 kV, 130 kV and above voltages, these equipments are no more useful because dielectric withstand capability of the equipment. Okay. So now, if you go to the higher voltages like 11 kV, 33 kV, 66 kV, we require some special relays to detect such fault. That is called relays. For higher voltages levels, it is difficult to install the protection device along with the switching device on main bus or line. So relays are connected to the secondary of CT and VT so that it will collect the CT current information in the line and as well as voltage information in the line, and it will monitor the system voltage and currents and send trip command to the circuit breaker on fault condition. Relays are only sensing devices, not the switching devices. In this 33 kV or more than that voltages. But if it comes to the lesser voltages, fuses, MCB and MCCBs are protection devices as well as switching devices. But if you go to the higher voltages, circuit breakers are only switching devices, and relays, the combination of relays and as well as CTs, VTs, those are just measuring devices and sensing devices of faults. Here you can see the different types of relays, that is electromagnetic relays, static relays, numerical relays, and mechanical relays. So electromagnetic relays or types of like current relays will be there, voltage relays will be there, frequency relays will be there, power relays will be there. And later they come up with the static relays where we're having the definite time over current relays, indefinite time over current relays, step relays, and as well as distance relays. Oh, these all are come up with the static relays in the 1970s or somewhere. Then later they introduced numerical relays. These are the latest version of the relays. Can have one numerical can have multiple protection functions and as well as control functions and as well as metering functions. So this is the main advantage of numerical relays, that can be available with different protections like differential protections, then transformer differential protections, RF protections, bus bar protections. There is number of types of relays will be there, and the manufacturers will be ABB, Siemens, then the TND, GE. These are the main manufacturers of the numerical relays. And mechanical relays mainly used in transformers where you are identifying the Buchholz conditions, winding temperatures, and as well as oil temperatures. For this, we are using thermal relays and as well as the other mechanical relays. Now, as I discussed earlier, the main components in the protection system for 11 kV and more than 11 kV voltages, voltage transformers and current transformers, these are required to monitor the line voltages and current voltages, because the voltage transformer can convert, suppose if you are going with the 11 kV systems, voltage transformers are it will reduce from 11 kV voltage to the 110 voltages, which can be suitable for meters or protection devices. And similarly, current transformers, the primary line current, if it is a 4000 amps, your metering equipment, you can't connect directly to this 4000 amps, so that we are converting from 4000 amps to the 1 amps or 5 amps secondary, and the secondary current is connected to the your relay. And as well as relays, the main functionality of the relay in this protection system is it will convert the received voltage inputs and as well as current inputs, and it will check with the predefined settings in the relay. And if it is if the values are crossing to the predefined settings, then it will detect that fault and the contact get closed, and it will send trip command to the your trip coil of the circuit breaker, and your circuit breaker will trip for the faults in the system. Okay. And next one is the DC batteries, because trip coils, like your system should be continuity in operation all over the time, so that we should give non-break supply to the trip coils as well as monitoring of these trip circuits and all. Okay, so that AC supply like 230 volts AC or 110 volts AC is not allowed for the tripping circuit and control circuit. That's the reason in all over the world, every country they're using either by 110 volt DC or 210 volt DC or 48 volt DC. They're using as a control and auxiliary supply for trip circuit as well as control circuit operation. Okay. This is the complete arrangement of protection zones in the power system network and substation. As I told earlier, from like the complete power system is connected from generating stations to the distribution, or finally it will be connected to the end user. So that we need to protect each and every piece of power system. How we are maintaining that is by doing the overlapping of protection zones. If you check this, first I started with generator, then I'm calling upon, like I'm fixing here generator protection, then there will be station bus bars, then I'm fixing with LV bus bar protections or LV switchgear protections, then there will be a transformer, then I'm overlapping with the bus bar protection with the transformer protection, then again there will be a substation. So like this. So if you check this, just I'm each and every place I'm overlapping one protection zone with the next protection zone, so that I'm not leaving even small portion of the power system to I'm not leaving even small portion of the power system, because if you leave that, if there is any fault in that particular zone, that we can generally we can call it as a blind zone. If there is any fault in that blind zone, no protection will operate, so that your system will get failure. That's the reason whenever you are doing the protection system design, you should be very clear that all the protection zones should be overlapped with next protection zone, so that we can cover 100% protection for the substation or for the complete protections power system in the substations and TND. And here I'm listing out the universal nomenclature of the protection functions. So if you check, I think in this forum, many people are worked in site for higher voltages. You can see this in you can might be observed some numbers in the protection relay schematics, that is like 21, 87, 87B, 87L. Okay, so these are the universal nomenclatures that we are generally following all over the world, and some especially we are following this nomenclature in India, and some other countries they are following just text instead of suppose if you consider the distance protection, I'm using in India they are using nomenclature as 21, but if you go to the other countries like Finland, Russia and other countries, they are not using 21 as a designation, just they are mentioning that distance protection, like the text they are using as a nomenclature for the particular protection function. But in India, if you check anywhere in the India, they will follow this nomenclature in the system design as well as the protection design in the schematics as well as the relays. And generally, if you consider any substation, there will be some typical base. So that is line feeder, then transformer feeder, bus section, bus coupler. Okay. So based on this, we can discuss how we are going to provide what are the protection functions to be considered in the line base, transformer base, and bus sections and bus couplers, and as well as the bus bar protection. We can discuss one by one. And generally, if you, in the protection system, only there will be two types of protection. One is unit protection, and second one is non-unit protection. Unit protection is the protection system that is designated to operate only for the abnormal condition within a clear, definite zone of the power system. In this picture, if you can see this, CTs are connected on the both end. So my relay connected between these two CTs. If there is any fault from this point to this point, then only this relay will operate. If the fault is beyond this point, this relay will not operate. So this we can call it as a unit protection. Unit protection is nothing but in-zone protection. The best example for in-zone protection is current differential protection. Like you can say that busbar protection, transformer differential protection, REF protections, or cable differential protection. These all are comes into the unit protections. And the unit protection schemes are based on Kirchhoff's current law. That is, some of the currents entering in the area of the system must be zero. Any deviation from this must be indicate an abnormal current path. In these schemes, the effect of any disturbance or operating condition outside the area of interest are totally ignored, and the protection must be designed to stable above the maximum possible fault current that could flow through the protected area. And unit protections can be applied throughout the power system, and since it does not involve any time grading, it is relatively fast in operation. The speed of response is substantially independent of the fault severity. Second will be non-unit protection. The non-unit schemes will also intended to protect the specific areas have no fixed boundaries, as well as protecting their own designated areas, and the protection zones can overlap into the other areas. While this can be very beneficial for the backup purpose, there can be tendency for too great an area to be isolated if a fault is detected by different non-unit schemes. As like if you check here, if there is any fault, this relay is not detectable because this is operated only for in-zone fault. But and also this unit protection, it will not act as a backup protection for any outside faults. But the advantages of the non-unit protection is it can protect the first zone area, like some area, and also it will act as a backup protection for the next protection zone as well. So that time grading, current grading capabilities will be available in non-protections. So generally non-unit protections will be like time graded overcurrent protections and as well as distance protections. These will all come into this non-unit protection. Is there any queries up to this point?
Sir, I have wondered
Yeah.
because the distance protection we are considering as a unit protection or non-unit protection because
Non-unit protection. Yeah. Why it is a non-unit protection is, as I told, the differential protections. Okay, the differential
yes,
protection can be called as a unit protection because that will operate only on the particular zone. You are considering
okay,
two cities, and if there is any fine differential current in that particular zone, then that will relay will operate and it will trip the two circuit breakers on the two areas. But distance protection is, it will start from the section A and it can grade up to 80% of the protected line, then 120% of the protected line, or 180% of the protected line. So it will not have any fixed zone. You can extend the zone by varying the impedance values or the current operation times. Okay.
okay.
Yeah.
That
So
means only we have differential and RF protections as a unit protection.
yes, wherever the protection, bus bar protection, you are
Bus bar protection
yeah,
also.
bus bar protection, you are collecting cumulative currents in the particular zone. Okay, then if there is any
Okay,
differential current you found in that area, then the relay is called upon for tripping. But the distance protection or overcurrent protections, it will be not like that. It will not taking any secondary, any other remote end currents, and it will not calculating for the protection operation. Only it will
okay,
collect voltage input, current inputs. Based on the current it is sensing in the device, it will give tripping command to the your circuit breaker. Okay, it will not compare with
okay,
the currents in the other end. So that we can't
okay,
say distance protection or overcurrent protection as unit functions. Those are non-unit protections.
okay,
Okay. Yeah.
okay, sir.
Sir,
Yeah.
sir, one doubt, sir.
Yeah.
What blind zones
Yes.
in previous slide? You say
Yes.
blind zone.
Yes.
Yes, sir. Please describe.
Yeah, blank
What?
zone is nothing. Blank zone is nothing but, for example, just 1 second. Just I will take something. Just let assume that this is your one substation, and you are carrying this, and this is your other substation. Okay, let
Yes, sir.
assume this. This is one particular protection zone, and this is my other particular protection zone. Okay, your relays are fixed here, and relays are fixed here. For example, Let assume that this is one and this is one. These two are connected for one relay and these two are connected for one relay. Okay. So in this condition, if there is any fault in this particular area, okay, these two cities will sense that fault, and the protection which is there in this area, it is going to operate and it will trip the circuit breaker here. Okay. And similarly, as this CT is looking this side and this CT is looking this side, and relays are connected in between, so that if there is any fault in this particular area, this relay will operate. But come to this point, which protection will going to operate now in this case?
No one, sir.
No, right? So this zone, we can call it as a blind zone. Okay. So how we are overcoming these blind zones is just you are taking this and you are taking this, and let assume that you are having this kind of, okay, now, and as well as this side. Okay. So let assume that you are having here one more city, here one more city, and this is one city, here one city, one city, one city. Okay. Now how I'm overcoming this blind zones is just I'm going to take this. This is my line protection. Okay. And this one, this is my this one, and this is my bus bar protection. Then this CT and this CT, again my bus bar protection, and these CTs, it is going for feeder protection. Okay. Let assume that this is your bus bar protection
Yes.
and this is your feeder protection, and this is your again bus bar protection, and this is your again your feeder protection. Now, for example, if there is any fault is here, your bus bar protection is going to operate. If there is any fault is here, both bus bar protection and as well as feeder protection is going to operate. If there is any fault is here, your feeder protection only will operate. Okay. This is how I'm overlapping my protection zones to overcome the blind zones, so that in any place from up to this point to this point, in any place, if there is any fault occur, my protection relay will operate and it will trip the necessary circuit breakers. Okay.
Okay, okay, sir.
Yeah. This is about the blind zone concept.
Sir,
Yeah.
sir, I have one wonder. Is it
Yeah.
mandatory to overlap the protection zones in every cases?
Yes. It should
Because
be
in
mandatory. It should be mandatory.
because in some of the cases when we are doing the GAS, then we don't have sufficient code to overlap these protection zones. Some cases at the time, how we can
In that case,
compensate this?
generally that's the problem. If you go to this 11 kV and 33 V switch gates, you don't find in the 11, especially in the 11 kV switch gates, you don't find any bus bar protections. You can find only overcurrent and earth fault protections.
Yes,
Okay.
yes.
Protection. In that condition, there won't be any there won't be any backup zones or overlapping zones. But the protection functions which included in that particular area, that will be setting. The settings will be placed. It can avoid the it can avoid the maloperations when the fault is beyond the dead zones, and it will be settable in the safe, like the settings will be is like that it will operate if there is any fault within that particular area. So it will be that can be overcome based on the settings for 11 kV and 33 kV voltages, because the 11 kV switchgear cost is around, it is 5 lakhs. But if you go to this 66 kV and 110 kV, the cost of the system, it will be more than 1 crore. Okay. So in this, if you are not protecting your system properly, then you are keeping your 1 crore into risk.
Yes.
66 kV, 132 kV, and as well as 400 kV, 765 kV. These all are very important voltage levels, because in these all the substations are interconnected. If there is any problem with one feeder, then it is going to impact on power supply to the next feeder as well. So that it is very, very important to ensure that all the protections should be overlapped if you are going with more than 33 kV voltages, because it is a interconnected system. But 11 kV switchgear, 415 volts, these all are self-user equipments. If there is any problem with that 11 kV switchgear or 415 voltages, that problem is only limited to the user. It will not impact on the other user. Okay.
Yes, 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 sir.
Can we go to this feeder line protection?
Yes, sir, sure, sure.
Yeah.
Yes, sir.
Okay. Now, as I discussed in the earlier, for 11 kV, 415 volts in these areas, overcurrent and earth fault protections can be used as a main protections, and that too when we're having that lower distance of the transmission line. As the length of the transmission line increases, overcurrent earth fault protection alone are not enough to protect the system due to speed, sensitivity, selectivity criteria. Due to this, for higher voltages and transmission systems, line differential and distance protection can be used as main protection, and overcurrent earth fault protection can be used as backup protection. In the main disadvantages in the overcurrent and earth fault protection relays are that there will be a time grading, but which is not sufficient to protect the transmission line, which is more than 2 kilometers or 4 kilometers or more than that. So that's the reason we are going with differential protections, distance protections to save the like to monitor the complete length of the transmission lines. And backup earth fault protection is applied to all the feeders to enable the detection of high resistance earth fault. For those feeders where two-unit protections, two-unit protections is nothing but where you are having two differential protections or two line differential protections are applied, a three-phase overcurrent backup protection is also to be provided in addition to the backup earth fault. This ensures backup protection provision for any uncleared face-to-face or face-to-earth remote bus bar or mesh corner faults. Backup earth fault protection in certain scenarios can be the only protection that will help to detection of open circuit conditions on the feeders. In parallel circuit, the imbalance caused by single phase open circuit conditions on a circuit may be insufficient to cause the unit and non-unit protection operation on the faulted circuit. But the system backup protection is expected to operate to clear that imbalance in the system. In those cases where high maximum load and minimum fault conditions dictates, such as some photovoltaic generations, it may not be possible to apply backup overcurrent protections. For such cases, it is necessary to substitute the overcurrent protection by integral non-unit protections in the main protection. Backup protection arrangement deploys in two unit protections, which is with the integral of non-unit protection in each unit protected, IED shall be provisioned. In all instances, zone 1 shall be disabled with the backup protection provided by other zones 2 and zone 3 and reverse zones. So it means that whenever, for example, if you consider the transmission lines, you are providing one unit protection and one non-unit protection, but unit protection is operated based on the current input, but the non-unit protection like distance protection is operated based on the voltage input. But because of some site constraint, it is not possible to install VTs, voltage transformers. So as voltage transformer is not available, you can't apply distance protection to protect the system, because the distance protection is purely operates on voltage input and as well as current input. As voltage is not there, you can't provide distance protection into the operation. So in that case, how we are mitigating that is we can include one differential protection, and backup protection function can be considered as overcurrent and earth fault protections. Whenever you are having transmission line less than some kilometers, you can have both unit protections, like main one as a unit protection and main two as a unit protection. That is, main one is differential, main two is differential, and you can integrate non-unit protection function, that is distance protections, into these two unit protections. And in that case, Zone 1 protections should be make it disable, and zone 2, zone 3, and zone 4 can be operated based on the time levels. So these are the characteristics of overcurrent. If you check the main characteristic of the overcurrent, there will be four characteristics. That is standard inverse, very inverse, extreme inverse, and last standard inverse. So standard inverse is nothing but when the fault current is high, it will trip immediately. When the fault current is low, it will take some time to trip the circuit breaker. Very inverse is nothing but like if you're having maximum peak fault current, then it will give instantaneous trip to the protection. And extreme inverse is also related to the same like, but that exact values can be calculated based on the equations I listed here. Sorry. Okay, now we can discuss one by one each protection functions which is used in line transmission line. So first we can call upon line current differential protection that can be described as 87L. That is the ANSI code which is used around the world. So line current differential.
Sir,
Yeah.
hello, sir. Sir,
Yeah.
what is the meaning of the high resistance earth fault, sir?
Sorry, come
Means
again.
in the previous high resistance earth fault, sir.
Yes, yes. Just I'll explain that. See, 1 second. Let us assume that this is your transmission tower. Okay.
Okay, sir.
And you are running your transmission lines here. Okay.
Okay, sir.
And here you are having some insulators.
Okay.
Okay. Let us assume that whenever you are having the fault conditions in the system, okay. So because of
Okay, sir.
these fault conditions, if the insulation of this insulator got failure, sometimes there is a chances. Okay. So in that case,
Okay.
what happen is this fault current, whatever the fault current it is flowing in this transmission line, it will be connected to this tower, and from the tower it will be got earthed. Okay.
Yes, sir.
So
Yes.
this we can call it as a line to ground fault. Okay.
Okay.
This
Yes.
condition. So the total resistance in the transmission line in that fault, we can say that it will add the resistance of your transmission line. Okay.
Yes, sir.
Then resistance of your
Insulator.
tower.
Insulators. Insulator and towers.
Yes. So in this case, you are having additional resistance. It is appearing into the fault current. That is because of this tower.
Yes,
Okay.
sir.
So this we can call it as a high resistance earth faults. So when you are having high resistance earth fault, sometimes the distance relay you can't you can't like distance relays. These distance relays are not sufficient to detect this resistance earth fault because you are not sure when you are giving when you are selecting the settings in the distance relay, because the settings purely depends on impedance values of the transmission lines. Okay.
Yes, sir. Yes,
But
yes.
when you are selected some 80% of the impedance you selected for the protection operation, because of this fault you are having additional resistance into the system. Okay. So
Yes, sir.
that
Yes.
it may become 82% or 83%. So in that condition, this relay, it will detect the fault and it will trip the circuit breaker, but it can't mention exact location of the exact location of the fault because of these additional resistances. So that's the reason to detect this high resistance earth fault, we're employing backup earth fault. Okay. So this earth fault is generally having suitable setting parameters to detect the earthing of like resistance of the towers in addition to the transmission lines, and it will trip the circuit breakers.
Okay.
Okay.
Okay, but sir, they not provide the distance, na, sir? Backup earth fault. Yeah, provided the distance, sir. Which
Backup earth fault, it will not provide the distance information, but it will since these kind of faults this fault can be sensed by backup earth fault as fast when compared to the distance relays. Because
Okay, sir.
distance relays, the sensitivity of this high resistance fault will be very less because of these additional resistors.
Okay, sir. Understood.
Okay, and to
Okay, thank
mitigate,
you.
suppose we're having backup earth fault protection and also we're having a line differential protection. Okay, so line differential
Okay.
protection, it will purely operate on the differential in the current, entering current and leaving current. It will
Yes,
not
sir.
matter about the impedance or resistance in the transmission line. So this also will be works as fast as compare to the distance protection to identify these faults and as well as backup earth fault. Okay, so that's the
Okay,
reason
sir.
whenever you are calling upon two non-unit protections in the transmission line, the backup protections must be backup earth fault
Okay, sir. Understood.
to detect these high resistance earth faults. Okay,
Okay, sir. Thank you, sir.
yeah.
Clear, sir.
Okay. Now, just we'll discuss about line differential protection. So, line differential protection relates operate to difference in entering current, like the current into the line compared to the current out of the line. This is called the current differential method. Okay, the differential current can be measured in different ways. One is magnitude comparison, then phase comparison, and phase or directional comparison. That is, we can say that magnitude and angle comparison in the relays. And also relays communication, because when the transmission lines are connected beyond 2 kilometers, it is very difficult to connect both hardwiring connections between the two current transformers to the relay. So that's the reason what we can do is when we are having the more transmission length is more, we can install two different relays at two different locations. For example, this is substation A and this is substation B, where I'm having the CT that will be connected to the 87L, and similarly at the remote end also from the CT I'm connected to the 87L. But between these two relays, I will provide the communication link, so that at each and every seconds, like not in seconds, it will extract the information from one end to the other end, the current inputs, so that this relay, it will collect the input relay current input from the remote end, and it will compare with the local currents. If there is any difference in that current, then the relay will operate and it will give trip command to the circuit breaker at the local end. Okay, that's the reason communication path is very it will be very important when you are using differential current protection in the transmission line.
Sir,
Yeah.
if remote in any interrupts, and then also local
Yes.
relay or circuit breaker are open,
Yes.
sir.
Yes. So that how it will operate is, so suppose for example the fault is somewhere in the protected line. This protection will operate. Okay, and it will give the trip command. It will send inter trip to the remote end relay. Okay.
Okay, sir.
So in the remote end relay, it will receive the inter trip and it will give tripping command to the your circuit breaker. That intertrip can be sent via this communication link. So there will be a protection signals, there will be a current signals in the communication path. Both will be sent in different channels.
Okay. Sir,
Okay.
in local and remote in between, in any fault, then which relay will be operated, sir?
Yeah. For example, if there is any fault in this communication channel, okay. So in that case, it will wait for 3 seconds. If the communication channel it is not reverted back to the normal condition, then first it will give alarm condition. Then the 87L differential protection will block. It will not operate, and backup protection will come into the picture. In that case, if there is any fault is happened in the line, your backup protection will operate and it will give the trip command.
Okay, okay, sir.
Okay.
Okay, sir.
If suppose if the system engineer when they're doing the system studies and when they're doing the relay setting calculations, and based on the fault current level of fault current at the substation. If the backup protection operated time, if they believe that if the operation of the backup protection, it will be more to mitigate this fault, then what they will do is, if the communication channel is failure, irrespective of whether it is a fault in the transmission line or not in the not fault in the transmission line, it will go for a tripping of the circuit breaker. Okay, because the differential protection is purely works on current inputs from the local end as well as the remote end. If you are not receiving the current from the remote end, then this main protection will not be operate. So that also will consider as a one type of fault, and it will go for tripping after 3 seconds. Okay.
Okay, sir.
Yeah. Now coming to this non-net protection, that we can call it as a distance relay in this. So like differential protection can be used as a first main protection, and a distance relay can be used as second main protections when you are going two main protections in the transmission lines. That selection of whether it is a how we can select unit protection or non-unit protection, that depends purely on the length of the transmission lines, that I will explain in the coming slides. So if in the distance relay is nothing but in the distance relay compares the current and voltages in the relaying point with the current providing with the operating torque, and the voltage provide the restraining torque. In other words, an impedance relay is a voltage restraint over current relay. For a fault at the far end of the line, the local voltages is the IZ drop in the line. Therefore, the voltage to the current ratio of such fault will be Z, where Z is the impedance of the line. For a fault internal to the protected section, that is V by I is less than the Z, and for fault beyond the protection section, V by I is greater than Z. The V by I ratio at the relay can be termed as the impedance seen by the relay. The relay will operate if the impedance seen by the relay is less than the Z. Since the impedance seen is directly proportional to the length of the transmission line between relay to the fault, it is also measured as a distance to the fault from the relay point. And hence such relays will which compare the voltage and currents are called it as a distance relay. So in other words, in simple words, how we can mention it is, at the local end, it will collect the CT input as well as the VT input, and they will determine the impedance of the relay point, that we can call it as a V secondary and I secondary. That will compare with the predetermined setting voltage. So generally, if you go with the relay protections, the distance relay, we can mention it as a zone 1, zone 2, zone 3. If you are setting zone 1 as 80% of the protected line, then it will compare 80% of the ZL with this Z scene. If Z scene is less than to that particular value, then we can go with the tripping of the circuit breaker.
Sir, wonder.
Yeah.
Sir, can you explain that point with parameter values? Because how
Yeah.
it will
1 second. See,
detecting the impedance?
yes, just I will open this. Okay, let us assume that this is one transmission line where I am having CT and as well as VT. Okay, this is my relay, that impedance relay, where I am collecting my CT input and as well as my VT input. So in the inside relay, it will calculate Z. So Z is nothing but V by I.
Yes,
That is
yes. Okay.
okay. And let us assume that the fault is happened here. So this is
Okay.
like 100% of the transmission line. Let us assume that this is
Okay.
100 ohms. Okay, from starting point to the 100%. But my fault is here. Like as first setting will be Z1. I will select. Okay, Z1 I am selecting it as a 80 ohms. Okay. So when the fault is happened, for example, my fault is happened at let us assume that this is up to 80%. The fault is happened at 60% of the
Okay.
transmission. So that when the fault is happened, your current and VT will be collected here, and this will sense the voltage on current. So that Z relay point will be V by I, that is 60 ohms. Okay, this is
Okay.
less than my Z1 setting. So that
Okay.
I assume that the fault is inside my protected zone.
Inside one.
This will go
Inside.
the circuit breaker.
Okay.
Understood?
Yes. Yes.
Yeah. Okay. Now,
Hello.
yeah, please.
How we can define the predefined value settings? How it can be defined? It is
See,
um,
this spread how, like if you check the distance relays, there will be a zones of protections. Okay, zone one, zone two, zone three. Okay, you are
okay.
having the transmission line, and the transmission that may be ACSR conductor, that will be available. Okay, so that manufacturer will give the total impedance of the transmission line, based on the conductor material. Okay, so
Okay.
that I will take it as a basic evidence, and based on that, I am going to set 80% of the protected line, that is 80% of the ZL. Then
Okay.
Z2 will be 120% of my protected ZL, or 122 or up to 150% of ZL. Then Z3 will be 150% of my protected line plus 120% of the next shortest feeder from the other end substation. Okay, here my parameters will be like, here I'm defining that zone 1, zone 2, zone 3, because zone 1, my ultimate aim is I want to clear faults in my line, protected line. Okay,
Okay.
so that can be achieved by selecting the 80% and 120%. That's the reason when 80%, when zone 1 is operated, because here I am sure my fault is within my protected zone, so that it will call instantaneous trip to the your circuit breaker.
Okay.
But
Mhm.
come to this Z2. Z2 is 120 to 150% of the protected line. That may be fault in within my zone, within my protected line, or the faults may be available in the next area as well. Suppose if you consider the fault is here in the other end substation, this also comes to total 150% of the ZL, because 100% you are completing here, and also you are extending, for safer side, you are also extending your protected zones to 50% to the next transmitted line. Okay, if the fault is here, then Z will be sensed here, so that operating time of the Z will be 500 milliseconds, so that I am giving some gap to trip, because if the fault is cleared within this 500 milliseconds, I no need to trip my circuit breaker.
Okay.
Okay, so this, why we are using this kind of phenomena is to interrupt the power, like to interrupt to the powers to the other users, and also as these are the interconnected systems, you can't trip unnecessarily of the circuit breaker if the fault is not within your protected line. Okay, that's the reason we can call this as a time graded protection philosophy, the distance protection.
Okay. Okay, sir.
Okay.
Okay.
Yeah.
Okay, sir. Why not Z1? We are not taking 100%.
Because here also I'm having the protections. So for example, if you consider this end, if you have, this also, if you're having this one, but if you consider, even if you consider the 100% of the protected line, okay, that also it will come with overlap with your busbar protection zone here. Here, as I told, right, here I'm having the line protection, then there will be also busbar protections.
Yes.
Okay, if you consider 100%, then the fault, that limit, it will also go to the bus section, like the bus bars. Why I need to trip if the fault, if the suppose if the fault is somewhere here, and if the my one of the user, they're collecting supply from this transmission line, if there is a problem with this busbar protection, I don't need to trip my this circuit breaker, so that I can deliver continuity power supply to this user by tripping only this circuit breaker in case of busbar fault.
Mm.
Okay, so to maintain this, they are going with 80%, 120 to 150%, then 150% of the protected line plus 100% of the next shortest feeder. So that is time grading. Zone 1 will be instantaneous, zone 2 will be 120, like zone 2 will be 500 milliseconds, zone 3 will be again 1 second. Okay, and I will also discuss some more concept. We can call it as a PUTT and POTT. That is permissive underreach tree, underreach, and as well as permissive overreach. So there you will get idea exactly how it is operating when the like how we are considering 100% of the protected zone by using this PUTT, the permissive underreach tip. That I will explain in the next slides. Okay.
Okay.
Yeah. So now we can discuss about the types of distance relays and the characteristic curves which is available in India as well as the outside. So that will be impedance relay. So the impedance relay is nothing but it will be based on the voltage and current input parameters, and based on that they will form the one circle, the operation of circle we can say. So in this, if you check this is your resistance and this is your reactance of the transmission line. By using this, we can have the complete circle. We can say that if the fault is happened anywhere in this circle, it will operate, the relay will operate and it will trip the circuit breaker. But let's assume that the main disadvantages is the my fault is somewhere here. That's okay because this is your transmission line, and the fault is happened here. You can trip the circuit breaker here. That is acceptable. But let's assume that the fault is somewhere here. This is outside of your protected area, outside of your transmission line. But the relay, as the relay is the operation condition of this relay is because of the circle characteristics, the fault is here, then also it will trip the circuit breaker, so that we can use power supply to the other end user, as even though the fault is on the even though the fault is not on the transmitted line. So to overcome, yeah.
So how we are plotting this circle? Can you explain that one?
Yeah, that purely based on the resistance values and reactance parameters. For example, just if I consider this, this is your R and this is your X. Okay, this is transmission line 1, this is transmission line 2, and this is transmission line 3, and let us assume that transmission line 4. So sorry, just leave about this. This is R and this is your X. Okay, let assume that this is your line 1 and this is your connected line. Okay, let assume that you are having the circuit breaker here and you are having the circuit breaker here. This plot is purely based on the resistance and Rx values. For example, let's consider the resistance ohm 1 ohm, reactance 1 ohm, so that I will take the point, this one. Okay, now let us assume that my zone protection is 80% of the protected loan. Okay, so that I will consider 80 of the relay and as well as reactance also 80, so that that point will come here. Okay, by taking 0 as a reference and by using by using this, I will draw the entire circle. Okay, so by using the parameters of R values and X values, this plot will be drawn. In this case, okay, if the fault is somewhere here, as this fault is within this circle, so that it will assume that the fault is within the protection zone and it will give this circuit breaker as well as this circuit breaker. And similarly, for example, as this fault is here, the protection relay also will be available here. This will operate and this will trip the circuit breaker. But as the relay whatever you provided here, is with these characteristics.
So, sorry to disturb you.
Yeah.
We can't see your cursor, sir.
1 second, I will make it. Just I'll take. Yeah, now we can see that yellow color.
Yes, sir.
Yes, sir. But
Okay.
bit larger.
Yeah, I think this is the problem with this particular one. Just I will take the black point. Now you can see, right?
Yes.
The blue color. Blue color. Okay.
Yes, sir. Yes, sir.
Let assume that you are having the CT here and my protection relay is available here. Okay. Now my protection relay is provided with that impedance characteristics where I'm having this plot circle, so that as relay is available with these characteristics, even the fault is on the other end. Okay, this relay will sense this fault and it will give trip to this circuit breaker before operating the circuit breaker here. Okay, so because of this I am losing my as the circuit breaker is tripped, I connected my circuit this transmission line to the other substation B. I am losing this power supply to the this substation, so that this will impact on other line transmission line which are connected to the users. Okay, so this is the main disadvantage of this circuit.
Sir, one doubt. Because if the fault is happening on the left quadrant, but at the time there is already we have provided a circuit breaker on the left side also.
Yes.
Why that one is not tripping? Because as per the time grid.
Here also the same thing. That's the problem with this plot circle, this circular characteristics. So this will sense all the faults within this particular zone. This will consider as a one zone. So in that zone again, there will be a zone 1, there will be a zone 2, there will be a zone 3. As the fault is here, this circuit breaker also will trip, and also this circuit breaker also will trip, because this relay also will sense. This relay is available and this relay is available. At a time for this fault, both relays will sense because of this circular characteristics.
So again one doubt, because in the transmission line, whenever there is taken the RX curve, because R is in the x-axis and X is considered in the y-axis.
Yes.
But normally in the transmission, the resistance value and the reactance value generally not a same value, right? That will be some difference. Then that shape, how the shape is becoming circular.
That's the reason I'm telling. See, the relay manufacturer, okay, whoever may be, whether it be ABB or any other one, they will select they will collect the inputs from the this one, like R values of the transmission line and as well as the X values of the transmission line. Based on that, they will give inputs to this relay. Okay, there will be setting parameters to plot this circular. Okay, these values will be entered in this particular relay, so that the plot will be drawn inside the characters will be defined inside that. So the main input for this circle is R and values of the transmission, that will be taken actual values of the conductor which you are using in the transmission.
Yes. Actually, that R and reactance and resistance values are provided by ourselves, right?
Yes.
We are giving the conductor resistance value or in case the reactance value.
Yes, that will be that's the reason whenever you are doing the relay setting calculations, the like relay setting engineer, they will ask the inputs of R values and X values.
Okay. The R value means the conductor resistance, and the X value is the positive.
Conductor resistance, and as well as X values of the transmission line.
Means positive secant reactance, that values.
Yes.
Positive, negative.
Yes.
Okay.
Okay.
Okay, sir.
Then, so as this is the advantage to mitigate this, we are going with the directional impedance relay. So in the directional, this is like a 1 second. Yeah, this is the non-directional relay, so that it will operate forward zone or reverse zone if the fault is there in that particular section. So to mitigate that, then we are going in the concept that directional relay, so that the portion of this area can be reduced to the forward direction only. For example, if the fault is somewhere here, then only this relay will operate, then it will trip the circuit breaker. Okay, so that if the fault is somewhere in this area, now this relay won't operate because of these characteristics, directional characteristics. So directional characteristics will be selected based on the flow of fault current. If you consider the same again circle, okay, if the fault is happened here, the fault current, it will flow from this point to this point, so that the CT will available here, it will sense the direction of the current, then it will call for the trip. But in the same area, if the fault, for example, if the fault is here, current, it will not go from this point to this point, then the fault current, it will go from like this, so which is opposite directions to the your actual direction of the current, so that your relay will not operate for this fault. Okay.
Sir, I have one doubt.
Then which relay will operate, sir, in this opposite direction part?
1 second. So as I told, just let me remove this. Let us assume that your circuit breaker here, your circuit breaker is here, and CT here one impedance relay, CT here one impedance relay. Okay. So now let us assume that, as I told, the fault is here. Okay. So this relay is settable in a such a way that if the fault current is in this direction. Okay. So that if the fault is here, this relay will operate and it will trip this circuit breaker. But in this fault condition, the fault current, it will flow from this direction, so that this relay will not operate, because this this relay is set in the direction of current should be like this. So how I'm taking this is, let us consider this is substation A and this is your substation B. Okay, the current will be connected like this, so that here one relay is there, here one relay is there, and similarly, if you consider this is one circuit breaker, and it will be connected to the other end circuit breaker. This is one. Here CT will be there, and here CT will be there. So that this is one protection zone. This is one protection zone. This is one protection zone. So that the relay which is connected here and relay connected here. So this relay will took the direction of this, and this will look the direction of this, and similarly this relay and as well as this relay, it will took the direction of this and it will took the direction of this, so that if the fault is happened here, the fault current from the bus bar, it will go like this, okay, to this fault area, so that this relay will operate and it will trip the fault current. But in this case, in this the fault, if you consider the AF, these the fault current, it will extend from in this direction, but this relay is meant for operate for the forward direction. As this is the reverse direction, this will not operate, only this circuit breaker will operate and it will trip the circuit breaker. Okay.
So at the time, how the relay can understand that the direction? Like, is there any provision to add the directional element, or like?
Yes, in the relay, that's what I'm telling, right? The plots will be drawn in a such a way that will be like, as I'm here, you can see this plot. Z1, Z2, Z3. So these will be considered as the forward directions. By using these, they will consider only this portion. Okay, this is the your operating zone. The direction of
but
element will be set it in the direction that based on the your positive sequence values and negative sequence values and zero sequence values.
but in this curve is starting from the left quadrant.
Yes.
Right. But the bus is actually located in the zero quadrant, means 0 0 coordinate.
Yes.
But in when we are drawing the graph like a 180-degree angle, then we are taking the left quadrant also.
Yeah, that will be again how we are taking is that one. Let's assume this. Okay, here this is my operating curve. Okay, sorry. For the faults happened here, okay, that will give instantaneous trip to the circuit breaker. But let us assume that this is here and the fault is here. For this, here there will be like as I told, there will be zone 1, zone 2, zone 3. Okay, and also there will be reverse looking zone. Okay, this reverse looking zone for consideration, I have this settable value. So that will be considered some 20 to 40% of other shortest feeder which are connected to this bus bar. So in suppose if this relay is available here, but unfortunately this relay is not operated. You need some backup, right? Otherwise, the fault current may extend to this one as well as it will damage the system. So that what it will happen is zone 1, zone 2, zone 3 reverse zone will be there. In this operation condition, zone as the fault is here, zone 1 will not operate, zone 2 will not operate, zone 3 not operate because these three are forward looking zones. But the fourth zone will be there, that is called reverse looking zone. This reverse looking zone will sense this particular fault, but there will be a time grade called 1.5 second. Okay, if the fault is not clear within this time, reverse looking zone will operate and it will trip your local circuit breaker. To consider the reverse looking zone, you are having this portion of information. Okay.
Okay, but who will decide the angle beams?
That's based on the impedance diagram.
Impedance diagram means the first circle diagram.
Yes.
That one.
Yes, you are providing, right? That we see you are considering R value and X value, and you are having the transmission line. So based on this, the tan inverse of X by R, they will calculate that.
Okay.
Okay.
That will get the effective impedance value, right?
Yes. Yes. Yes.
Sorry to jump in. Is it possible that the theory part the doubt part we take in the last and first the flow of the class, let it go, Rahul?
Yeah, sure.
Let him complete the today objective. In the last 20, 15 minutes, 30 minutes, we will have the Q&A. In that, all the doubt that you have note down, and in the last one by one, we can discuss all the doubts so that the flow will not interrupt.
Sure, sir, sure.
Okay.
Yeah. So when Gopal, like you go through with your today objective, and in the last, all participants will have the queries, and then one by one you can take up.
Yeah, sure. Okay.
Yeah. Okay.
Thank you. So next I will go to the other type of relay we can call reactance type relay. Okay. So in that reactance relay will measures VI by sine theta, that is Z sine phi. Whenever the reactance measured by the relay is less than the set value, the relay will operate. The operating characteristics of that RX diagram are shown here. So this is your operating region, and beyond this, if there is any fault is happened, then the relay will not operate. The next kind will be Mo. So the Mo is nothing but designed to operate only for the directional element, which is just slight modified than to the directional impedance relay. So this is how it will operate. So here we're taking as the 0 as the origin. By using that, we're just by using the values of R and X, we're calculating the values and we're drawing this operation. So here, where as I discussed earlier, this is the just advanced version of the directional relay. It will operate zone 1, zone 2, zone 3, and there will be some backup provision that we can call it as a zone, reverse zone. Similarly, the offset relay is also just having some offset information to the more relay. Then nowadays, the widely they are using quadrilateral characteristics. So that will be universal accepted characteristics of the distance protection. It will be suitable for forward zones of operations and as well as reverse zones of operation for remote tripping, as well for the initiation and as well as the blocking tripping. So it means that whenever the fault is happened on the forward looking zone, it will operate and it will trip the circuit breaker. And if there is any fault happened on the reverse looking zone, that will send intertrip to the remote end by saying that the fault is not in the protected line, so that block your tripping, so that the remote end circuit breaker, it will not trip. So for distance relay, there will be several factors which is going to affect the setting parameters of the distance. That is the impedance of the value. So in that, one is the fault resistance. So fault resistance as the arc resistance and the arc resistance and the ground resistance. For normal fault, the total impedance of the transmission line is R plus JXL, that is ZL. Due to the presence of fault resistance, the impedance measured by the relay is R plus Jx plus Rf. The Rf is nothing but the fault, like whenever you are having the arc in the fault, that resistance also it will add to the Zr. So when the Zr is greater than Zl, the fault resistance in the line, the length of the arc, then I will be the fault current. So arc resistance has little impact on Z1 as Z1 operate instantaneously before the arc can quench. Arc resistance has more impact on the other zone settings and the operating zones. That will be the RR will be given the formula here is here. Then second thing is branch effect. So when as a fault in the branch effect, if you consider that, generally this will be calculated based on these transmission line parameters and other area where this will be calculated based on the other one. But when the fault is happened here, then the circuit breaker is tripped. Because of this parallel impedance, it will also affect on your Z parameters in the this line, so that the protection may mal-operate or it may mal-operate when the fault is beyond its zone. Okay, so that's the reason nowadays what they are doing is instead of going with the 80% of the selection for zone 1, they're going with the 75%. The 5% they're reduced because of this branching effect. Second one is in-feed effect. The effect of intermediate current source between relay location and fault point is termed as the in-feed effect. Consider the following example: a fault on the F and the BC line, that is distance from Z1 plus Z2 for the relay at the station A. But when current I2 flows from the D, when the current is flowing from this, then the impedance of the fault seen by the relay is at A is equal to Z1 plus Z2 plus Z2 into I2 by I1. But if you don't have this particular one, let us assume that if there is a fault is happened and you trip the circuit breaker, then your I2 is not going to impact on this particular zone selection. In that case, the total impedance of the line will be reduced to the actual value of running. So that also to be considered when you are doing the relay setting calculations. Next one is source impedance ratio. So just source impedance, one second, yeah. The source impedance ratio, just I will take this and I will explain so that you will understand more. Let us assume that this is your ZL and this is your ZS, the source impedance, and this is your relay point. Okay, this is your IL, and this is your IR. So this is your V relay. Okay, so for me, V relay is equal to current seen by the relay IR into impedance of the transmission line. But if I want to calculate the IR value, that will be V, that is the voltage of the transmission line, Vs divided by Zs plus Zl. Now if I added this value to this particular one, then VR is equal to Vs by Zs plus Zl into Zl. If I take this to the numerical value, then Vs divided by 1 plus Zs divided by Zl. Okay, so this is your VR, like voltage seen by the relay. If as denominator Zs by Zl, if the source impedance is more, then this value will be more, then voltage across the relay will be very less, so that your distance protection relay is that is not sufficient to detect these kind of faults. So that's the reason the generally the source impedance nothing but if you're having the transformer. Okay, if you are having the transformer, that is if you are having the 400 by 130 kV transformer, the Z will be 80%, 8% of the impedance will add. Okay, as is this the Zs is more and Zl is less, so that this valve will be more, the voltage across relay will be less, so that it will not the relay will be less sensitive to detect the faults in the transmission line because of this additional impedance. So that's the reason whenever you are having the high source impedance, distance protection is not suitable for the protection operation. So in these conditions, what we are doing is, instead of providing the distance protection, we can go with line differential protection plus overcurrent and earth fault backup protections. So that we can call it this. We can Zs by Zl. We can call it as a source impedance ratio. So here, if I just read this, the application of distance protection to the short feeders requires careful consideration in terms of its performance. Non-unit protection performance is impaired when it is called upon to operate for the power system faults resulting in very small voltages and currents. These faults conditions generally arise when non-unit protection is applied to the short feeders with relatively low fault in feed, that is high source impedance, as I discussed in my just now. The performance criteria required to reach setting accuracy limit is 5%. Maximum zone 1 operating time will be 30 milliseconds. For system impedance ratio is values up to 30 seconds. So it means that when if you're calling this one, when the source impedance ratio is up to 30, then your operating time will be 30 milliseconds. Percentage of error will be 5%. And if you are crossing the source impedance ratio from 30 to 60, then your protection relay may operate like you can't give guarantee up to 10% of error. But when your source impedance ratio is between 0 to 30, then the secondary values of the voltage and the currents will be the 5% error will be there. And if you go to this 30 to 60, there will be 10% error, which is not good good for considering the distance protection relay operation. So that this relay may mal operate if you are going with the distance operation. To avoid that, we are going with line differential protection and overcurrent and earth fault protection as a backup. Okay. Now come to this. How we are selecting unit protection and non-unit protection based on the transmission line length of the transmission line. So as I told in the earlier, up to 33 kV, that is for 14 volts AC, that is the LV switchgear design, and as well as MV switchgear design. MV switchgear is nothing but 6.6 kV voltage, 11 kV voltage, and 33 kV voltage, where we are using overcurrent and earth fault protection as the main protection, so that there won't be any other backup. Whenever it is operated, it will call that the relay will operate and it will trip the circuit breaker in this 33 kV switchgear. Come to 66 kV and 130 kV, where unit protection is applied when the length of the transmission line is less than 10 kilometer, and a unit with non-unit will be integral if the transmission length is between 10 to 30 kilometers. And if the transmission line is exceeding 30 kilometers, then you are going with non-unit protection as a backup. Sorry, non-unit protection as a main protection, and backup will be overcurrent and earth fault protection. Okay, but if you go to this 275 kV and 400 kV levels, here two main protections will be there and one backup protections will be there. The backup protection may be integral of the main protections or standalone entity. Okay, now here also the same like 60 kV, 130 kV. If the length of the transmission is less than 10 kilometer, you are going with unit protections. Both are unit protections. And if you have the transmission line is between 10 to 30 kilometers, one will be the unit protection and second will be the non-unit protection. Then if the transmission line is exceeding 30 kilometers, then we can go with main one protection as a non-unit protection and main two protection as a non-unit protection with integral of backup earth fault, because here overcurrent protection is not required. The same will also applicable for 400 kV. So this is the selection parameter for national grid, which is UK, which is slightly different to the Indian grid. But in Indian grid, you can see this the length of the transmission line like 100 kilometers, 200 kilometers also you can see. But in the national grid, if you check the national grid, the maximum length of the transmission line is 50 kilometers. If you allow the in UK, if you check, the maximum length will be the only 50 kilometers, but in India it will go like 40 kilometers, 50 kilometers, 80 kilometers, 100 kilometers, sometimes 200 kilometers also. Some transmission lines are constructed here. So in the national grid, how they are doing is, if the length of the transmission line is less than 4 kilometers, they're going with both are unit protections. And if the transmission line is length between 4 to 10 kilometers, then they're going with first may protection as unit protection, second will be the blocked distance scheme. If the length of the transmission is between 10 to 50 kilometers, that 50 kilometers is the maximum length. So they are going first main protection as a unit protection, second main will be a non-unit. As like India, if once you are crossing the 30 kilometers, both main protections will be non-unit. The like main one distance protection and main two distance protection. But in the national grid and as well as the other countries, main protection irrespective of the transmission line, the first protection will be always line differential protection, and second protection will be a distance protection or non different line differential protection. When transmission line is purely cable, that is if the two substations are connected by using the cable instead of the overhead line, then both protections will be unit irrespective of the irrespective of the cable length. Both will be differential protections. Even in India also the same, and as well as other countries also same. And also the cable length also it is going to place in the transmission line. For example, if you consider the two substation, 80% of the if you consider the total 100% of the distance, 80% they covered by using the OHL and 20% covered with cable. So in that case, the selection of unit protection or non-unit selection, that will be based on this parameter. If the cable length in the total transmission length, if it is reaching more than 20% of the total transmission length, then you should go with unit protection. If the total cable section in the overhead line that will be less than 20% of the total 100% line, then you can go with non-unit protection. So this is the Jones selection in distance protection. As I discussed earlier, Zone 1 will be 80% of the zone, 80% of the transmission line. That will go for instantaneous stripping. And zone 2 will be 100% of the zone line. This will be like, they will mention it as 100%, but at the actual conditions, you need to consider uh, total 120 to 150% of the ZL you need to consider. Otherwise, you can also consider 100% of the your protected load and also 40 to 50% to the next shortest feeder which is available in the same bus area. And zone 3 will be 100% of the zone L, like the protected line, then 120% of the shortest feeder which is connected to that particular bus. That will be operating in between 0.6 to 0.8 second. And zone 4 will be 100% of the protected line and 120% of the longest line which are connected to this bus. So longest and shortest is nothing but, for example, if you consider you are providing relay here, okay, the zone 1 will be from this A point to B point, 80% you need to consider. Zone 2 will be 100% of A to B, that is from this point to this point. And if in this, this is like one substation, okay, here there will be multiple feeders. So you need to find out the shortest length of the feeder. For example, from C to D, there is a one transmission line that will be, that you can consider that 100 kilometer. From similarly, from C to E, suppose if there is any substation E, if the transmission line connected between C to E, that is having 120 kilometers. In that case, for zone 3, you need to consider shortest feeder, right? So in that case, you need to consider the transmission line between C to D. For longest feeder, you need to consider from C to E. So based on that, you need to select the zone 1, zone 2, zone 3 for the operation circuits. And as I told earlier, in the offset more relay and as well as quadrilateral characteristics, there are also zone 4. Sorry, zone 5 will be there. Okay. So zone 5 is nothing but reverse looking zone. Some conditions and some manufacturers, they will provide zone 1, zone 2, zone 3 and zone 4 as reverse looking zone. And some manufacturers will provide all four zones will be forward looking zones, and fifth zone they will add it, and that will be back reverse looking zone. So as I told, distance protection scheme can be operated in different ways. So that will be like plain distance scheme, blocked distance scheme. Then there will be a permissive underreach transfer trip and permissive overreach transfer trip. So that I will explain through. Okay, let us assume this. Okay, so what I will do is just I will explain the plane. So plane is nothing but Z1, Z2, Z3, and I'm considering Z4 as reverse zone. Okay, as I explained in the slide, so Z will be 80% of the transmission line I'm considering. This will be 120 to 150. And this will be considering 100% of the protected line plus 120% of the shortest feeder. Then this will be, I'm considering 40 to 60%. As I told, this I'm considering as a reverse zone. Just I'll mention reverse, all will be forward. 40 to 60% of the shortest line which is connected here. Okay. So now in the plane distance scheme is nothing but, for example, the fault happened here. So that is, this is if you consider the 80%. As the fault is within the protected zone, then zone 1 will operate and it will give instantaneous trip to the circuit breaker. That is, operating time will be 0 second. Once the fault is identified, immediately it will give trip. Z2 will be then 120 to 150% of the protected. For example, the fault is happened here. So this will comes to 120 to 150% of the time, so that it will operate after 500 milliseconds. Then zone 3 also forward millisecond, forward one, Let assume that this I'm connected to the other shortest feeder. Then the fault is somewhere here, okay, which is in this particular zone. That is the one additional 120% which I'm adding, right? The fault is in that case, okay, or anywhere in this spot. Let's assume that this will operate after 1000 milliseconds. And similarly, zone 4. So zone 4, suppose for example, the fault is somewhere here or somewhere here. That is my reverse looking zone. In that condition, this may operate after 1.5 milliseconds. Okay. As the fault is here, just you need to understand here is as the fault is at F. This is 80%. So zone 1 will start and zone 2 will start, zone 3 also will start. But
Z4 is 1.5 millisecond or seconds?
milliseconds. Sorry, 1.5 second. Thanks. Okay. As the fault, if the fault is on the transmission line, that is under the 80%, so that zone 1 will operate because the fault is within this 80%, within this 80%. And similarly, zone 2 will start, but it will not give trip because the timer will start as the fault is at the 60% of the transmission line. For example, this is at 60% I'm considering. So 60% is in this value only, so that Z2 timer will start. Similarly, Z3 timer also will start. But before expiring of these two timers, I'm giving trip to the circuit breaker and I'm tripping so that these timers will be reset once the circuit breaker is tripped. This is the plain scheme. Now, if you just, I will go with the blocked distance scheme. So blocked distance is nothing but, just I'll take this. Let us say substation A and substation B. Okay, here I'm having relay. Also here I'm having relay. Here also I'm having relay. Here I'm having relay. Okay. Now, again, in the block distance scheme, what will happen? Again, for example, here if I consider this zone 1, zone 2, zone 3, and as well as zone 4, that is reverse looking zone. Okay. Let assume that what is the block distance scheme is nothing but, suppose if the fault is in the protected line, zone 1 will operate and it will trip instantaneously, that will operate. Zone 2 and zone 3 timers also it will operate. But for example, let us assume this. This is zone 2, right? So zone 2, 80% you are considering, and zone 2 I am considering 120 to 150%. So let us assume this. If the fault is somewhere here, okay, if the fault is somewhere here, so that the relay also is here, like in this relay also, zone 1 will be there, zone 2 will be there, and zone 3 will be there, and also zone 4 reverse will be there. Now, as the fault is here, which zone will operate now in this case? Three zones are forward looking zones. So it means that if there is any fault in this direction, it will sense. And zone 4 will be reverse looking zone, so that as the fault is here, the zone 4 will be, that is 20, we can say that 20 to 40% of the feeder which is connected to this one, so that here Z4 will activate. Okay. So as the Z4 activated, it will send, it means that this relay will send information to this relay so that Z4 is operated. So what it will do is, once the Z4 is, once it is received the Z4, because here the Z2 is operated and also it received the Z4 signal, so that it will form the AND gate. Zone 1, zone 2 is operated. I received the zone 4 signal from the remote, so that output it will send that block the trip. Okay.
But before activating the zone 4, the the zone 1 protection at the bus B, that will be activated, right? Because compared to the zone 1 for the B.
That's correct. So that's what I'm telling here. If you suppose if you consider zone 1, as the fault is here, okay, during the plane condition, what will happen, irrespective of the remote end condition, zone 2 will operate after 120 to 150, so zone 2, as the
Yes.
fault is in the zone,
Also,
after 500 milliseconds, you are tripping the circuit breaker. Now, what I am doing is, as I am receiving the zone 4 signal from the remote end, okay, once the zone 4 it is operated, immediately it will send signal to the A end, so that it will stop the tripping of the circuit breaker. As
yes.
this will, the zone 1 is operated and it will trip the fault, so that you no need to trip the circuit breaker. So to avoid,
Yes.
I am sending blocking signal to this end. Okay. Similarly, when the fault is happened here, this relay will send blocking signal to this relay to trip this circuit breaker. Okay. This is called blocking signal. Now, let me go with another scheme. That is permissive underreach. 80%. Okay. Now let me check here. The fault is here. Okay. This is your 80%. So that here zone 1 will be there, and zone 2 will be there, and zone 3 will be there, and zone 4 will be there. So here also the same thing. Zone 1, zone 2, zone 3, and zone 4. So here I am discussing is called permissive underreach trip. Now what will happen is, as the fault is here, zone 1 will not operate, right? Zone 2 will start, okay? And here zone 2 will start and zone 3 will start, and as well as zone 4 is if we reverse direction, this will not start. So just I'll check, it will not start. This also will not start. But in from this end, if you consider the B end and this is your A end, at the end, zone 1 will start, and as well as zone 2 will start, zone 3 will start, zone 4 will not start. Okay. As we are having the communication between these two relays, what it will do is at the local, as it is zone 1 operated, so zone 1 will be instantaneous trip, so that it will give instantaneous trip to the circuit breaker. And similarly, zone 1 signal will send to the remote end, that is A end. So in the remote end, what it will do is zone 2 operated, and as well as I received the zone 1 signal from the remote end. This is from the remote end. So if both conditions are met, it will give instantaneous trip to your circuit breaker. So by using this, what I am getting the benefit is I am just overriding the zone 2 operating time, that is 500 milliseconds. In normal conditions, after 500 milliseconds only, we are tripping the circuit breaker. But by using this permissive underreach scheme, zone 2 operated from this end and other end zone 1 is operated. It means that the fault is within this protected zone only. It means that the fault is within the protected line only. So I'm having that 100% evidence by collecting this zone 1 information from the remote end, and it is checking with the zone 2 operating at the local end. Then you are overriding that 500 milliseconds to 0 seconds, and you are tripping instantaneous trip to this circuit breaker. This is called permissive underreach trip. Okay. Next. Permissive overreach trip. So in this permissive overtrip is nothing but, again I'll go 80% substation A, substation B. I'll consider one numerical relay here and consider one more numerical relay. Again, the fault is same location. Okay, here Z1, Z2, Z3, and Z4 reverse zone. Just I'll mention Z4. Here also the same thing, Z1, Z2, Z3, and Z4. So as the fault is here, that is at 90%, I can say, from the substation A, but from the substation B it is 10%. So that if you check that at A, Z1 will not operate. Z1 yes, timer is started. Z3 yes, timer is started. Z4 will not operate. Here yes, Zone 1 is operate, and also Zone 1 will start the timer, and Zone 3 will start, and Zone 4 will not operate. As Zone 1 is operated, it will give instantaneous trip. As I discussed in the earlier, for permissive under reach, what I'm collecting is at local end you are selecting the zone 2 operation at local end, and from the remote end you are receiving zone 1 signal. Then you are checking this condition and you are overriding this 500 milliseconds and tripping TB after 0 seconds. Okay, but in the permissive overreach scheme, what we are doing is at local end zone 2 operated, I mean zone 2 started, and from remote end also we are taking zone 2 signal. So if both are correct, then also we are overriding TP0, because from this end, if you check that the fault is within in the zone 2 area, and this end also the fault is in zone 2 area. It means that there is a common point. It give clear indication that the fault is in the protected line, so that we are considering the zone 2 at the local end, we are collecting the zone 2 information from the remote end, and we are overriding the zone 2 timer at the local end, and we are tripping instantaneous trip to the circuit breaker. This is called permissive underreach scheme. Okay, so permissive underreach and permissive overreach both will be used in the transmission lines uh, to protect the 100% of the protected line. Okay, so generally most of the cases in the India, they will select permissive underreach scheme, because it will give 100% clear information that the fault is going to have the fault information in the protected line. Okay, and block distance schemes they will use mostly whenever they're having short distance line, that is from 2 to 10 kilo we can say 2 to 10 kilometers. So that what will happen is the most of the times zone 1 reach will like zone 2 reach, it will go beyond to the substation B. Okay, so for the faults on the substation C, you need to trip faults of the for substation like the just I'll take this. This is substation A, and substation B. This is your substation C. For example, as this is the very short distance line, this the fault at the remote end substation may create unnecessary tripping to the circuit breaker. So to avoid this, we are using blocking scheme whenever you are having shortest distance line. In remaining cases, we are using permissive underreach scheme in the distance protection to clear the faults and to protect the 100% of your transmission line. Okay, and so second, and along with this main protection that I discussed, like main protection will be line differential protection and as well as distance protection. That selection also I explained. Now along with this, the backup overcurrent and earth fault protection is also I explained. So, along with these three protections, we are also having multiple functions which are inbuilt in the numerical relays that we'll discuss one by one. So in that, first one will be feeder end protection. So if I go here, feeder end protection, let's assume that this is your transmission line and you are having CT and CT. Okay, this will be looking for bus bar protection and this will be looking for feeder protection. Now let's assume that the fault is here. Okay, so when the fault is here, your bus bar protection will operate and it will trip the circuit breaker. Okay, and let's assume that this circuit breaker is connected at the remote end B. So in the normal condition, this is also in closed condition, this is also in the closed condition, and power is feeding from this end to this end. Now, as the fault is appeared here, your bus bar protection is operated, and you are trip the circuit breaker, and you are not like bus bar protection operations. Bus bar protection can mute. Okay. So, Raghu, is my idea is clear?
Yeah, clear. I think someone else unmuted. So others you can mute. Like Umesh Majhar, please mute Majhar. You can mute others.
Yeah, just 1 second. I'll do
You
that.
have the control, so you can mute all.
Okay, I'll do it. Okay. So in this condition, what it will happen is, as the busbar protection is operated, it will trip the circuit breaker, but the busbar protection operation it will not send intertrip to the remote end to trip circuit breaker. Fault is not cleared, and also feeder protection it will not operate because the feeder protection CT is looking forward direction. So in this condition, what will happen is we can have feeder end fault. Okay, so the feeder end fault protection, what it will do is, after the busbar protection operated, if the circuit breaker is tripped, and if the still after the CB is opened, and they will collect CT input, output will give trip to the remote end. So it means that busbar protection is operated, circuit breaker is opened, and your feeder protection is not operated because for feeder protection the fault is beyond the zone, so that it will not operate. So in that condition, I want to clear this fault. How I should do is, I need to send this information to the remote end by using intertrip. So by using this intertrip, remote end relay will receive this intertrip signal and it will give tripping command. So how I am sending intertrip signal is, so as CB is open and the CT is measuring the fault current still. So if both conditions are met, then it will send feeder end fault protection is operated signal to the remote end, and it will trip the remote end circuit breaker as well, so that fault will be cleared. Then there will be a power swing block. So that also is the part of your main protections. So distance relays have the functions to detect the power swings in the system and block the tripping of the CB. As change in the impedance seen by the relay at power swings is low as compared to the real fault in the system, because when the real fault is happened in the system, there will be a sudden spikes in the currents and as well as voltages. So that will consider as a actual fault. But when you are having the power swings, for example, if there is any addition and removal of loads in the transmission lines, so in that condition there will be sudden changes in the currents and voltages. So relay should not trip for these conditions. So this to be considered as power swing blocking. And also VT fuse failure. As I told in the earlier, distance protection is operated based on the voltage input. If the voltage input is not there, then your distance protection is relay is not going to operate. So that's the reason we need to provide VT supervision function in the relay. So what it will do is it will monitor the secondary circuit of the VT. If there is any faults or loose connections in that secondary, if the voltage is less than that 110 by square root of root 3, then that will consider as a VT phase failure, and it will block the operation of the operation of the distance protection, and it will also send alarm signal after 3 seconds. And similarly switch on to the fault. So if any fault in the system is identified by the relay and send trip signal to the circuit breaker, and it will see the CB gets tripped and clear the faults in the line. When line gets switched on to the fault condition, that is after the fault is fully cleared and you have to energize the circuit breaker, in that case you have to ensure that all the air switches, whatever the air switches you closed during the tripping condition, that should be open before energizing the circuit breaker and as well as the line. If if the site technician is forgot to open that air switch, then if the person is trying to close the circuit breaker to energize the line, then once the line is energized, immediately it will get tripped because of the air switch is already in closed condition. So it will create the triple line to ground fault. So this condition you are called as a switch on to the fault condition. Then stub protection. So stub protection is looks like similar to the feeder end fault, but the difference is stub protection will be connected, like stub protection will be interlocked with the disconnector status. That how is, just I'll mention this. As I told earlier, here will be the your line disconnector. But if you consider this is your circuit breaker and this is your line disconnector, but CTs are located here. Let us assume that this is your busbar protection and this is your feeder protections and CTs are located here. Okay, and the fault is here. So what it will do is during the fault conditions, what it will suppose for this fault, your busbar protection will operate and you tip the circuit breaker, and feeder protection will not operate because the fault is beyond the zone. So what I will do is for the maintenance purpose, I open this isolator as well. Okay, now I want to clear this fault. How I'm clearing this fault is just I'm taking the disconnector status, disconnector open status, then the CT. So if the CT measuring current is more than the actual rated current, it means that it is more than that setting value, then it will check the AND gate, then it will send inter trip to the remote end. So the stub protection, this is called stub protection. So feeder end fault protection is based on the CB condition and stub protection is based on the disconnector condition. Okay. Along with this, we also need to supervise the trip circuit because trip circuit is very trip circuit plays a major role in clearing the faults. Okay, so suppose if there is any fault is happened, the trip circuit should operate and it will give the trip command to the circuit breaker, and you should open the circuit breaker instantaneously. If you are not supervising, and if there is any suppose if the supervision circuit is not available in the system, there is a problem with the trip circuit, or there is a problem with the trip coil, and there is a fault happened on the transmission line, circuit protection relay it will give trip command to the your trip coil, but unfortunately as the DC supply failure in the trip circuit or trip coil is not operated, and your circuit breaker will not open, so that it will give very big damage to the system. So that's the reason before closing the circuit breaker we call and as well as after closing the circuit breaker, you need to supervise the circuit of trip coils. That we call it as a pre-close supervision and as well as post-close supervision. Pre-close supervision is nothing but before closing the circuit breaker, you need to check the healthiness of the trip circuit where you are having the trip coils and that connections. If everything is okay, then only you should give close command to the circuit breaker. So that is called pre-close supervision. Once the circuit breaker is closed, now system is in operation condition. This time also you need to supervise the trip circuit. That is called post-close supervision. Because before closing the circuit breaker, my trip circuit is healthy. I close it. But after sometimes, because of some issues, if there is any problem with the trip circuit, if I'm not supervising that, if the fault is happened in the circuit, if the real fault is happened in the system, this circuit will not operate and it will not give trip command. So to avoid that, we also need to supervise post closing of the circuit breaker. And if there is any problem with that trip circuit, you need to give trip to the circuit breaker irrespective of the fault conditions in the system. Okay, so that is a very important. Important is that you have to supervise this strip circuit both pre-close condition as well as post-close supervision. And when next one is pole discrepancy. Pole discrepancy is nothing but in 166 kV and up to 275 kV, some places the circuit breaker will be gang operated one. But if you go to these AI substations where we're having a 400 kV substations, the circuit breakers are single pole operated. So when you are having single pole operated circuit breakers, the close command the individual circuit breakers will be available on R phase, Y phase, and B phase. You need to close all the circuit breakers togetherly. You need to trip the circuit breakers togetherly. Otherwise, what it will happen is system will be unbalanced and that will give huge problems to the next feeders which are connecting to the particular station. So to avoid this, what we should do is you need to supervise the pole discrepancy function. So it means that pole discrepancy function is selected based on the auxiliary contacts of your circuit breaker. For example, as I shown in this picture, this is your positive 110 volt supply and this output will be connected to the binary input or any auxiliary relay which will give information that pole discrepancy operated. So how it will operate? For example, if you consider circuit breaker is, let us assume that circuit breaker is in closed condition. So when the circuit breaker is closed condition, all this NO contact will be get closed and NO contact will be opened. So in this condition, what it will happen? Positive supply will extend because all these NC contacts are NO contacts are closed, but supply it will not extend further because these three contacts are opened, so that your pole discrepancy will not operate. Now let us consider that R phase, Y phase circuit breakers are closed and B phase circuit breaker is not closed. So that what will happen is these two contact will get closed and this will be in open condition, and similarly these two will be open and this will be closed condition. So that what it will happen is supply will extend from these any of these two paths. Similarly, these two are in open condition so that it will not extend from these two paths, but the supply will extend from this path to the auxiliary relay, so that the relay will operate and it will give alarm signal by saying that pole discrepancy is operated. Okay, that is how the pole discrepancy function will operate. So these are the these are the typical way arrangements in the line feeders where you can see this. This is the one substation and this is the remote end substation where you are connecting two substation by using the cables. Okay, where the cable differential protection as like the line differential protection. When you are adapting the cable in between the two stations, you need to provide the cable fault because uh, if the circuit breaker is provided with the auto reclose functionality, you need to provide the cable fault detector because the cables generally buried in the ground or it will be passed in the tunnels from one station to the another station. So the faults happened in the cables will be mostly permanent faults. So during the permanent faults, you should not give auto reclose command to the circuit breaker. So to avoid that, what we'll do is we'll provide cable differential relay to detect the faults in the cable section, and also we're having a line differential protection beyond this point. So when you are going with the differential protection, if only over line differential protection is operated, then only it will go for the auto reclose. If line differential protection is operated as well as cable differential protection also operated, then it will block the auto reclose command to the circuit breaker. So this is the feed arrangements, and also second type of arrangements will be three stations will be interconnected: substation A, substation B, and substation C, and that will be connected either through overhead lines or through cables. That possibilities will be there. And here now I will take to the selection of relay. We can use the REL 670 relay and as well as RED 670 relay. So what I will do is just I will take to the RED 670 website, like ABB website, and I will explain how that is selecting.
Sir, please slow explain.
Okay. Okay. Just before going to this REL 670, just I will take to the questions. If there is any questions, please let me ask now.
I think we are done with most of the theoretical concepts, so we can take few protection SLD now. When
Yes, I
so
will do that.
whatever you have explained theoretically, so how those theoretical discussion is applied into a single line diagram, into protection single line diagram. If you take that point, so you can summarize all the
Yes.
theoretical discussion through the drawing.
Yeah, sure. I will do that.
Yeah.
So, what I will do is next I will share the one of the KPTCL like Karnataka Corporation Limited. I will take to the 132 kV substation, and I will explain the what are the how the single line how the key line diagram is built for the substation. So in this diagram, we are using the ANSI codes for the symbols like the protection functions. ATAC, ATDC, like AC supervision relay, DC supervision relay, distance protection, directional load current relay, that all are available in this particular one. So just I will take to the key line diagram. First, I will start with the 11 kV feeder protections, like 11 kV one. Then I will take to the 130 kV so that you will understand what are the changes from 11 kV to like medium voltage to the high voltage substations. As I told earlier, in the 11 kV systems, we are providing overcurrent and earth fault protection as the main protection that will be connected to the CT cores, which is having the measurement like protection core that is called 5P10 or 5P15 or 5P20. Okay, and these switchgear cubicles will be placed all the CTs, VTs, as well as circuit breakers will be enclosed in the switchgear cubicle, and control chamber will be provided on the top of the switchgear cubicle. So all the CT connections, VT connections that will be taken to the your relay, and whenever the fault is happened, the if a fault is happened in that particular one, that relay will operate and it will give trip command to the circuit breaker. So along with this overcurrent and earth fault protections, we are also using earth leakage relay to protect the like if there is any this is the cable section. So what I am doing is to if there is any leakage currents in the cables. So by using the CBCT, that is called core balance current transformer, I'm taking all the three cables into the CBCT, and if there is any leakage in that leakage in that cables, that will be converted and that will be connected to the earth leakage relay. So once the earth leakage relay is operated, here also I am tripping my circuit breaker. Here you can see this surge arresters I provided at the incoming of the switchgear cubicle, and also VDU. That VDU is nothing but instead of the voltage transformer, here I used voltage detection unit. So it will convert from one voltage to the another voltage by using the capacitor gradings, and it will give the indication of the supply availability. That is R phase voltage, R phase voltage availability, Y phase voltage availability, and B phase voltage availability. And along with this, I also providing multifunction meters and as well as trivector meters. So this will be very useful to measure the total energy imported or total energy exported to the user from the grid. So based on the energy parameters which is available in this TVM and as well as the multifunction meter, they will go with the revenue. Like they will calculate the total power what utilized by the user, then they will cost the amount based on how much they used. And similarly, ammeter, it will provide the indication of the current availability in the R phase, Y phase, and P phase. So how I'm selecting is by using ammeter selector switch. Whenever you are using digital ammeter, you no need of this selector switch. You can directly connect to the digital ammeter or digital voltmeter, so that it will give the phase voltages or phase currents without having the selector switches. And this will be the protection unit you are connecting, and wherever all the protection functions are listed here. So whenever the protection is operated, of any of this protection is operated, it will take to the tripping of this circuit breaker. And similarly, I also provided the control transformer in this 11 kV switchgear cubicle. Here, what I am doing is, this is the individual switchgear cubicle. Instead of taking 230 volts external supply for my heater circuit built in this panel, I'm just converting from the 11 kV to the 230 volts, and I'm using for my control supply. And from these 230 volts, what I'm doing is I'm converting from 230 to 110 volt DC, and that 110 volt DC I'm using for my tripping circuits. And these are the indication lamps which will give the status of your circuit breaker closed, circuit breaker open, and as well as the trip circuit supervision, as well as spring charge indication that will be available. And similarly, the TNC switch and local remote selector switch I provided. So local or remote selector switch, it will give indication that you can operate from the local as well as operate from the remote. So remote can be either from the substation control system or from the remote control systems. And TNC will be used whenever you selected the local operation. The TNC switch, it will give operate to the close as well as trip the circuit breaker. And similarly, the annunciator, it will give like I used to connect all the status indications to this annunciator. So whenever suppose CB closed, I connected to the one of the annunciator window. Okay, so once the CB is closed, that annunciator window, it will glow. That light will on in that particular window. So these are the specifications I followed for the 11 kV switch gear. And similarly, I also provided mechanical interlocks. So it means that in this switchgear cubicle, I'm having two incomers and one outgoing. So in these two incomers, one will be always in on condition, and another will be like standby unit. So for that, how I'm doing interlock is I'm providing two locks plus one key. So here I'm providing one lock, and here also I'm providing one lock, but only one key I'm providing, because if I provide two keys, what it will happen is one person will go and they will open the lock and they will operate, and one person will go open and lock operate. So that the paralleling operation will come into the picture. As I have not provided synchro check function here, that should be not allowed, the paralleling operation. So that's to avoid that problems, I'm providing only one key for the two logs. And this is the outgoing feeder. There are the protection functions I provided. Now it comes to this 130 kV protections. As I told earlier, 130 kV substations will be part of your interconnected systems. The overcurrent and earth fault protection is not sufficient to protect the transmission lines. So that's the reason what I'm doing is I'm providing one distance relay. Here, that is my first main protection, distance protection relay, and also I'm provided backup overcurrent protections along with that in the same numerical relay. But along with these main protections, I also provided directional overcurrent protections as per the specifications defined by the KPTCL. These specifications, like consider the protections for 130 kV substations are above voltages, that will vary from one state electricity board to the other state electricity board. If KPTSN can call for 130 kV substation distance protection, and backup will be only overcurrent and earth fault protection. And if you go to this PGCL and as well as Haryana electricity board, or Telangana state electricity board, or Andhra state electricity board, they may call different specifications, because that again they based on their system approach, how they built the substations in their connectivity, they will follow the different approach. Okay. And along with this, I also provided, along with the main protections, I also provided the TV trivector meter. Trivector meter, it will give the total energy parameters, as I told in the 11 kV switch gear, 11 kV switch gear. This is also common. This will be also used for revenue purpose. But whatever the CTs or VTs which connected for the trivector meter, mainly where you are going for the revenue purpose, that should have high accuracy of the secondary circuit. So that's the reason you are going with the 0.2 accuracy, and as well as the VTs also you are going with the 0.2 accuracy or 0.5 accuracy for meters. And for CTs, where you are going for the distance protections or new differential protection, you should go with the PX class. So the PX class should be you should be considered for line differential protections as well as for transformer differential protection or area protections, whatever may be the differential protections you are going or distance protections you are going. PX class should be mandatory because the CT should not saturate for the system fault conditions. because these faults you are going to, you have to sense the fault with having the more fault current, that is the transient faults will be there and permanent faults will be there, but transient fault will be like in terms of ks like 63 ka 100 ka 150 ka, sometimes it will come. So you have to find out that fault current, then only your relay will operate. Instead of that, your relay is getting saturated, sorry, your CT is getting saturated after 10 times of or 10 times or 15 times of to the rated current. So that secondary of your CT current, it will not provide the accurate values to the relay, so that relay will not operate for such high faults. So that's the reason you should not use 5P10 or 5P15 or 5P20 or 10P10 these general protection CTs for distance protections and as well as differential protections. And here I used the SF6 circuit breaker. So whenever the protection is operated, it will go for trip the circuit breaker. And similarly, I'm also supervising the AC supplies and as well as DC supplies in the substation. Whenever if there is a problem with the AC supplies or DC supplies, it will give alarm, and if the DC supply is not available, it will not allow the closure of the circuit breaker. If the circuit breaker is already in closed condition, if the DC supply is failure, then immediately it will go for tripping, irrespective of your the fault condition in the system. So this is about complete 130 level. Like if you go with the next 275 kV and as well as 400 kV substation, along with the distance protections, you also may come up with the second main protection, that is maybe a unit protections or non-unit protection, but operations will be more or less similar. So this is about feeder protections. So now the forum is open for Q&A. So if you're having any queries on these feeder protections or whatever the topics I discussed up to this, I will take now.
We have some questions in the chat box. So when you, could you see the chat box also?
Yeah, one second, I'll see that. Yeah, main and backup both are essential. Yes, suppose let assume that main protection having multiple functions inside, like differential protection or something. These relays are made of with electronic items. Okay, the electronic items may operate, sometimes may damage because of some overratings or some internal problems. Okay, if the main protection is failure, okay, you should have some backup. Otherwise, that will give a very big impact to the your system condition, and it will give damage to the your system. So to avoid that, what we should do is, along with the main protections, it is always to have one backup protections for safer side. Yeah, I will share this PPT so that you will get these ANSI codes for the protections. I listed all the protection functions which are used in these substations in the PPT. I will share that. I didn't get this PPC and grid analyzer. Ashok, can you brief about that?
Yeah, sorry. Actually, so I used to work in the UK, UK projects. So basically, we are using for PPC, grid analysis, and the power quality monitor. Okay, power plant controller for solar side and grid analyzer, and
Yeah.
these are the
The power quality monitor that I will explain. So
okay.
power quality monitor, why you require this? Let us assume that National Grid is if you are working in UK entity, there will be different areas. Like National Grid will be operating 130 kV, 275 kV, and 400 kV voltages. And below that voltages, like some of the 130 kV voltages, 66 kV, 33 kV, and below that voltages will be operated by SSEN or UK Power Network or some distributed network operator that we
The
generally
DNO,
call as
yeah,
a
yeah,
DNO.
yeah.
Okay. So what it will happen is National Grid operating with one protection policies or some policy statement, or they're having some dedicated standards, and SSEN they're following some standards. When you are integrating these two, okay, when you are integrating National Grid substations with user substations or DNO substation, you have to monitor the quality of the power which is imposed to the National Grid entity.
Okay,
National Grid
standard. Okay,
interconnection. Yes, okay. So,
okay,
for example, one user may generate some voltage with some power quality, and other user may generate power with some other quality. Without checking these power qualities, if you are imposing directly onto the National Grid entity, that will give big impact to the National Grid interconnected system. So, to avoid
okay.
that, National Grid and as well as the DNOs, they will have the bilateral agreement that we
All
can
right.
call as a connection agreement. Okay.
Oh, G99. Yes, yes, yes. Yeah,
Okay.
connection agreement. Yeah,
The connection
yeah.
agreement will be there. So in the connection agreement, they will very clearly describe that where the requirement of power quality meter and as well as a high accuracy meter that you can say ham unit. Okay.
Okay,
That also
okay,
they will clearly mention, and as well as harmonic disturbance recorders that also they will clearly describe in the connection agreement. Based on that, they will design the system and they will connect the systems. If that voltages and as well as power values are within that acceptable limit, then only they will go with the connections. Otherwise, they will call off the agreement.
okay.
Okay.
Yeah, thank you.
Yeah.
Uh,
Power plant controller is nothing but the CPU, where you are having the trip relay reset scheme and as well as circuit breaker close command and auto reclose command, sync check functionalities, all will be located in this power plant controller that we can call it as a CPU only.
And do we have any relation with the production release? Any input or output received from PPC for the
Yes,
relays
yes.
or something?
So
Oh,
for example, now if you consider the 400 kV substation, you are having connected to the one generation station. Okay. So
okay,
in the 400 kV is part of national grid, and the generating station is part of DNO or some user. Okay. So in that condition, the generator protections will be there on the generator, the DNO end, and feeder protections as well as other substation control equipment will be allowable in the national grid entity. So when you are doing the connection agreement between the national grid and as well as the DNO part, you need to exchange some information. Like what are the informations you need to exchange from is, suppose sometimes the protections of 400 kV, that line, whatever your line connecting to the DNO, that protection sometimes will be part of national grid, and
okay,
sometimes that will be part of your DNO network. Suppose if the
okay,
protections are part of your national grid entity, then they should share some this information like protection operated, bus bar protection operated, okay, CB
hmm,
close, CB open. These all signals will be sent to the DNO network. And similarly, DNO network has to say some of the information. For example, in the DNO network, the substation protection is operated, and the voltage values what they're generating at the generating station, and these values should be shared with these people. So that will
Okay.
be again that will be clearly listed in that connection agreement.
All right. Okay. Connection agreement. Yeah.
Yes.
Okay.
So in between the national grid and as well as DNO network, there will be one common marshalling cubicle that will call interface marshalling cubicle. So that is the
Oh,
common connection point between national grid and DNO network operate. So the whatever the inputs they are sharing from national grid to the user and user to the national grid, they will all will be connected to that interface marshalling kiosk and they will take the informations.
okay.
Okay.
Yeah. Thank you.
Cop meter based on the generation. Yes. So the cop meter, like whatever the metering you are mentioning here, the in the national grid they will have one standard. So we can call that is the metering code of practice. Okay, COP is nothing but code of metering code of practice. We can say that as a MCOP. Okay, when they're out in this MCOP, they define that if the connection, like if you are adding 100 megawatt, 100 megawatts or less than that, what are the protection classes to be considered? Okay, and what are the codes you need to follow, like COP 1 code, COP 2 code, or COP 3 code to be followed when you are having you are imposing 100 less than 100 megawatts of load. And similarly, when you are exceeding 100 more than 100 megawatts of load, then what the code to be indicated. So that will be clearly indicated in your connection agreement.
And one more thing.
Yeah.
So, like COP2 for HV, COP5 for LV, right?
Yes.
That COP2, right? The COP2, yes, we know sometimes COP2 always come with a CT. COP5, I think, had 200 amps. We no need to put CT. So, what's the logic between the relays to COP2 meter? Because we know, I know, like COP2 meter are using for like measuring the tariff and get the signal from the COP2 meter. So what's the logic behind between the protection and cop meter? Because I could see with some of the production diagrams like cop meter always cater with CT. Okay, so what is the reason we are putting CT in front of cop meter?
See, the COP 1, COP 2, or COP 3, again, that will be based, as I mentioned here, that based on the load, how much load you are taking or how much power you are imposing to the national grid entity. So if you are mentioning that less than 50 megawatts or 100 megawatts, based on that values, they define some standard values. Suppose that is called accuracy of the values. As like in India, we can have like 0.2 accuracy for one condition, 0.5 accuracy for one condition, 0.2s accuracy for one condition. Similarly, national grid also they follow the same concept. When your load is varying from one point to the another point, they will follow for 0.2. And if they're going for the revenue purpose, they will go with the higher accuracy, the 0.2s,
Oh, okay.
and 0.5 for your VT, and
Okay.
0.2 for VT for COP 1, where you are having
Okay.
more load.
So COP2 meter, we don't have any protection or something, right? So directly we can get
The
from the
code
CT,
of,
right?
code of practice that will be absolutely right. Code of practice will be different. So the in
Oh, okay.
metering code of practice, they will clearly define that. So the loads, variation of the
Depends on
load,
the loads.
yeah,
Yeah, okay.
load ranges, and based on that, you need to select the accuracy classes of the CTs and PTs. And again, one the thing is very clear that you should not include the CTs as well as VTs, which are used for the metering code. You should not share with the protection CTs, protection functions. So
Okay,
you should
okay.
have dedicated CT and you should have dedicated VT core for metering purpose.
Metering purpose. All right. Okay, got
And
it. Okay.
similarly, protection functions like differential protection or the unit differential protections, as well as the distance protection. Whatever the CTs you are using, you should not allow to share the CTs with metering functions or any
Protection.
other protection functions.
Okay. So,
Each protection functions have dedicated CT code.
okay. Sometimes we're confused. That's why I asked these questions.
Yeah,
Now
certainly.
I'm clear. Thank you so much. Yeah.
Yeah.
Thanks.
Yes. One is in-feed and branch effect of the distance relay. Yeah, just I will take you that. So this is like a branching effect. So when you are having the double lines from one substation to the other substation, then the total impedance seen by the relay, it will have the mutual impedance. For example, here you can say that during this the total impedance for the parallel circuit you are taking the Z total. Okay. Let us assume that the fault is happened somewhere here. Okay, and you are tripping the circuit breaker. Once you trip the circuit breaker, then let us assume that the relay is here. So during general condition, Z is considered based on this Z total. Okay, and here also the same thing. This is the Z total you consider based on the total the parallel impedance of the transmission line. But during the actual conditions, the ZL is measured only that this portion, like only one branch of the impedance. So that because of this parallel impedance, it will have some additional impedance will be imposed on this Z values, so that it will give unclear location of the faults, and as well as sometimes it may maloperate for the faults. So to avoid that, what we are doing is we are calculating this total impedance value, and we are having some compositions to the existing. So for example, let us assume that ZL1 is a real that line 1 impedance. Okay, as you are calculating the Z total impedance, you need to add portion of this information to this one, so that this is Z total. You need to add some percentage of the values to this one. That will be considered as the total ZL1 total ZL1 impedance for the calculations purpose, so that it will give accuracy of the fault locations as well as correct operation of the circuits. Then coming to this in-feed effect, here also the same thing. Let us assume that this is one. For example, this is the one case. This is one circuit breaker and this is one circuit breaker. The fault is happened. So when you don't have this particular one, your current, whatever the entering current, you are leaving here. So that the fault current and the current will be calculated very easily, and the total impedance will be calculated based on V by I. But as if you are adding new branch to the new line to this particular branch, then this current also it will going to impact on your total fault current. Okay, then this value may vary. Once this value may vary, then Z impedance also is going to vary. So that's the reason when you are defining the Z setting parameters, when you need to consider this branching effect as well as this infeeding effect to adjust these values of selection.
Okay, sir.
Yeah.
Okay, just one small query. Is it possible that could we have a class tomorrow in the daytime as well, like 2 session tomorrow? When you are like, what is your availability in the daytime?
Daytime.
Like 3 to 5, 4, like 4 to 6, or 2 to 4, like that. If you are available, then we will plan. Otherwise, we will go as per the regular schedule in the evening.
I think otherwise tomorrow we can have from. Yeah. Someone is.
No. Yeah. You tell when will this. Yeah, Jabir, could you please mute yourself? Yeah, yes, Venu.
Yeah, okay. Tomorrow we can go for the class from 2 to. Otherwise, in the morning is okay, Raghav?
I think actually few participant is from the UK as well, and few from the Ireland. Sukumar is from the Ireland, and Ashok is from the UK. So there are so many participants from the UK and Ireland, so they may not be comfortable in the morning shift.
Because in the afternoon I may not be available. That's the problem.
Okay, then no issue. Then we will go in the evening, like 8 p.m. like that.
Yeah, so okay, no problem. 8 p.m. is okay for me. 8 to 11.
8 to 11, yeah, 8 to 12, like that. We can have 4 hours, so we can have 2
Yeah,
hours,
sure.
5-10 minute break. Then again, we can take 2 hours like that.
Yeah, sure. We can start with 8 to 10. We can go, and 10 to 12 we can take. So after 10 minutes break.
Yes,
Is
yes,
that-
like that. Yeah. Okay. Okay. Thank you. Thank you.
Otherwise,
I want to.
can we do it one thing? In the afternoon only we can have from 2 to 6 instead of night. Is that possible? So that I will change my works to night.
I don't think that would be possible.
Yes.
If others okay, then I don't have any issue. Otherwise,
Yeah.
we'll go with as per the regular schedule. Let us go with regular schedule. Maybe.
Then we can connect by tomorrow 8 o'clock, and
Yeah,
I'll
tomorrow.
try to take up to 11 o'clock. If time permits, I will take to 12 also.
Yeah. Okay.
Again, Monday, everybody having the common work.
Yeah. Okay. 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 Thank you.
Thank you all. Thank you so much. Bye.
Thank you very
Sir,
much.
can we have some practical example of a schematic diagram of a
Yeah, sure. I will take that part as well.
so that we can understand this, like you said, that whole discrepancy relay connection, this time
Yes.
DC supervision on all
Uh,
that.
Yes, I will take all that part once I completed my theoretical concept on bus bar protection.
Please, sir, please. Yeah.
Bus sectionalizer. So once the theoretical concept is completed, I will take to the schematics of feeder protections as well as one of feeder protections. Then I will explain how
So that
the.
we can also learn that how to read a schematic diagram at
Yeah,
least.
sure. I will cover the topics as well.
Yeah, please.
Yeah, don't worry. I will cover that.
Venu sir, maybe sorry, actually, maybe it's a very early question. So
No, sir is required. You can call me Venu. No problem.
okay. So actually, because my question, so sorry, so you are going to cover. So like, today I have a little bit understand what are the relays are there. So you are going to teach me where you use for this relay, like 50, 51, 60, 680, all kind of relays. So going to teach me, right? This, if you are the prepare the protection diagram.
Yes.
So yeah, all right. Okay. Sorry. Thanks so much. Yeah.
Yes, like I think I've already covered where I'm going to consider the distance protection on this one. But remaining concept like that AC supervision, DC supervision, trip circuit supervision, this I will cover when we are going to the schematic part.
Okay. Got it. Yeah. Thank you.
Yeah. Okay, then thank you all. Good night.
Thank you so much.
Thank you, Venu. Thank you very much. Yeah, you make me the host now. You make me the host.
Just 1 second. I'll do that.
Yeah, thank you.
Yeah. Thank you all. Bye.
Okay. Bye.